Hello everyone, and welcome back to Prussian Blue Chemistry. Today is a great pleasure to host Dr. Tyler Weinhold from Florida State University. Tyler recently defended his PhD in the Friedrich group at FSU, where he developed elegant applications involving Tebbe's reagent in modern synthetic chemistry. In this seminar, Tyler will discuss recent studies involving Tebbe's reagent in dibromination and cyclopropanation, as well as its application in the enantioselective synthesis of fusicoccadiene, recently published in JACS. Tyler, thank you so much for being here with us today. The stage is yours.
All right, thank you, Louise, for the kind introduction, and thank you all for tuning in today. Today I'm excited to share some of the synthetic advances I've made using titanium methylidene. And I thought I'd start this talk off by just discussing sort of the general goals of method development. And so what are the goals of reaction development? Well, there can be several different goals. One might be novelty, so is the reaction doing something that cannot be achieved any other way. Might be versatility, so is it widely applicable in general. One might be selectivity, so things like regioselectivity, chemoselectivity, and stereoselectivity. Then there's also a practicality aspect to consider, such as scalability and affordability, as well as if the reaction is user-friendly. And I think methods that encapsulate all of these features can change the way chemists build complex molecules. And I think a really nice example of this is ring-closing metathesis. So ring-closing metathesis starts with a substrate that has two alkenes tethered and is catalyzed by metal alkylidene to form a cyclic alkene. And so this works by first forming a metallocyclobutane, which then decomposes to form a metal alkylidene intermediate, which reacts with the other alkene, forming a metallocyclobutane, providing the cyclic product. This reaction took years and years to develop, and one of the first developments was titanium methylidene. So what is titanium methylidene? Well, it's a titanium-based Schrock carbene. It contains two cyclopropanadienol, or CP ligands. It's nucleophilic at carbon, but also has a low basicity. And this reagent itself, titanium methylidene, is not very stable, and so it's usually generated in situ. And so there's two main ways to do that. One is with Tebbe's reagent, which is this titanium aluminum bimetallic complex and releases titanium methylidene in the presence of a Lewis base. The alternative is potassium reagent, which releases titanium methylidene by thermolysis at elevated temperatures, producing methane as a byproduct. And so the early work on titanium methylidene revealed that it engages in alkenes through a degenerate metathesis equilibrium, forming a Titanacyclobutane. And so the seminal work by Frank Tebbe, the inventor of Tebbe's reagent, found that reacting titanium methylidene with two alkenes, one of which is labeled with carbon-13, results in an exchange of the methylenes. And based on this observation, Frank Tebbe proposed the following mechanism, in which involves two Titanacyclobutane intermediates. In general, at low temperatures, this degenerate metathesis equilibrium favors the Titanacyclobutane. However, when temperatures are elevated, it actually reverts back to starting material. Now, the exception to this is in the case of strained alkenes, such as norbornene. In this case, Bob Grubbs found that norbornene reacts with titanium methylidene, forming the expected Titanacyclobutane. However, at elevated temperatures, instead of reverting back to starting material, a ring opening occurs instead, forming a new titanium alkylidene. This can then engage another molecule, norbornene, forming another Titanacyclobutane. This can undergo ring opening again, repeat this process, leading to the formation of a polymer. And so this is actually one of the first examples of ring opening metathesis polymerization, or ROMP, which is now a very vibrant field in materials chemistry. John Stille, while working with Bob Grubbs, was able to exploit this feature in his synthesis of capnellene. And so starting from this norbornene derivative and reacting with titanium methylidene can form the Titanacyclobutane. Then at elevated temperatures, carbonyl methylation occurs, followed by ring opening to form this titanium alkylidene intermediate. And that can then engage the nearby alkene, and after cycloreversion, provide the cyclobutene. This is then isolated as a ketal and further elaborated after a few more steps to complete their synthesis of capnellene. And so this is not only important for enabling the synthesis of capnellene, but this also represents one of the first examples of ring-closing metathesis. Now, when we consider all these objectives of reaction development, titanium methylidene being used for ring-closing metathesis kind of misses out on this versatility As we saw in this last example, a strained alkene substrate was required. And so to overcome this, Bob Grubbs ended up looking at other metal carbenes, specifically ruthenium-based catalysts such as Grubbs 2, to overcome these limitations. And his work on ruthenium-based catalysts, as well as the work of Chauvin and Schrock, led to them being awarded the 2005 Nobel Prize in Chemistry. And so where does that leave titanium methylidene? Well, it has its own application where it's commonly used for the methylation of carbonyls. And so this mechanism is very similar to the degenerate metathesis mechanism. And so the titanium methylidene reacts with the carbonyl pi bond, forming a four-membered titanocycle. This then decomposes to form the alkene, and owing to the oxophilicity of titanium, this process is irreversible. And now if we compare this to other olefination reagents, such as the Wittig reagent, titanium methylidene offers several advantages because of its low basicity. And so in this example, for the synthesis of canic acid, the methylation of the ketone proceeds without epimerization of the alpha carbon. However, when it comes to the degenerate metathesis of the alkenes and titanium methylidene to form titanocyclobutanes, work on that has been pretty much abandoned over the last several decades. That is until our lab came across a challenging transformation. I think one thing that's really fascinating about total synthesis is that it reveals unmet synthetic needs and therefore inspires new methods. And so here is a really nice example of this, in which a previous member in our group, James Law, was trying to methylate C7 of this substrate. And he tried, of all the known methods that he tried, none were successful. And so he had to develop something new. And so he turned to titanium methylidene to accomplish this transformation. And so he found that titanium methylidene can selectively engage this alkene to form a metastable titanocyclobutane, which then can undergo protonolysis to provide the hydromethylation product. And so our lab, after getting this finding, our lab was very excited about this, because not only could this not be achieved any other way, but this also proceeded with high regioselectivity, chemoselectivity, and diastereoselectivity. Therefore, we decided to develop this as a general method. And so just as a reminder, since this is going to continue to come up throughout this presentation, titanium methylidene is not stable on its own. It needs to be generated in situ. The way that we're going to be doing that is using Tebbe's reagent, and we're going to be using THF as the Lewis base to unveil titanium methylidene. And so at 0 degrees Celsius with Tebbe's reagent and THF, that reacts with the alkene, forming the titanocyclobutane. Once that's completely formed, we react that with a protic acid to form our hydromethylation product. And James found that several different substrates can undergo this process, including terminal alkenes, exocyclic alkenes, acyclic alkenes, and endocyclic alkenes. We also found that we can couple carbonyl methylation with this hydromethylation if we start from a ketone. And so if we use excess Tebbe's reagent, we can form the alkene in situ, and then with the remaining titanium methylidene form the titanocyclobutane, which is then reacted with hydrochloric acid to provide the geminal dimethyl product. And around the completion of this project was when I joined the lab, and I was really fascinated about this by this chemistry, but I was curious of how we could advance this chemistry even further. And so I kind of asked the question, like, what else can we react these titanocyclobutanes with beyond protic acids? And so in thinking about that question, I took a closer look at this protonolysis step for the hydromethylation. And based on how the titanocyclobutane is reacting with acid, I considered this intermediate as a 1,3-dianion synthon. And so based on this thinking, I considered, maybe other electrophiles could react. Could we react with, for example, halogen equivalents to form 1,3-dihalides? Now, I will say this is not completely unprecedented. There is one example described by Bob Grubbs in which he took an isolated titanocyclobutane, reacted it with bromine to form a 1,3-dibromide. However, for this example, which is the only example of dihalogenation, there is no yield or procedure reported. And so I wanted to investigate this process a little bit further. So I chose to use azetudenone as my model substrate and reacted it with excess Tebbe's reagent to form the titanocyclobutane, which I then reacted with bromine, and I found that I was able to selectively form the 1,3-dibromide. However, I also observed significant amounts of product B, cyclopropane. And to understand where this is coming from, we need to dig into the mechanism a little bit. And so the first step for both products is halogenation of the titanocyclobutane. The resulting halotitanium intermediate can undergo one of two pathways. Either it can undergo a second halogenation event, forming the 1,3-dihalide, or it can undergo an intramolecular cyclization to provide a cyclopropane. When the electrophile is switched to iodine instead of bromine, this is almost completely selective for the cyclopropane. And that's rationalized because the X group is now a much better leaving group, and so this intramolecular cyclization is going to be much faster. And so I've decided to turn my attention back to bromine since that was already selective for the 1,3-dibromination. And I wanted to figure out how can I make it even more selective. And based on how the halotitanium intermediate was reacting, the formation of product A would be a bimolecular process, whereas the formation of product B would be a unimolecular process. And so I thought maybe I could increase the rate of forming product A by increasing the amount of bromine present. And ultimately what I found is using 10 equivalents of bromine enabled almost complete selectivity for the 1,3-dibromide. With the 1,3-dibromide in hand, this could be simply cyclized with the primary amine to give a diazospirocycle. Now, diazospirocycles are interesting in the context of piperazine isosteres. So piperazine is one of the most common heterocycles found in over 100 FDA-approved drugs. There's been a lot of work done over the last 15 years or so where chemists are replacing the piperazine ring in a drug with a diazospirocycle, and as a result has an opportunity to optimize drug properties. These properties might include rigidity, solubility, or metabolic stability. And just as a very specific example of this, chemists applied this strategy to improve the properties of this FDA-approved drug, olaparib. And so by replacing the piperazine ring with the diazospirocycle, they were able to reduce off-target interactions while maintaining the drug's efficacy. Now, when it comes to the synthesis of these building blocks, these diazospirocyclic building blocks used to incorporate into drugs, there's really one main way to make these azididine rings, and that's just a simple substitution reaction. But it turns out each of these building blocks require several steps, at least 6 steps to prepare. And so we envisioned using this new dibromination as a way to develop a modular and concise approach to each of these building blocks. And so to do so, we started from commercially available cyclic ketones and reacted that with excess Tebbe's reagent followed by treatment with bromine provides the 1,3-dibromide. Important that this has the all-carbon quaternary center as well as the functional group handles to install the azididine ring. And so by cyclizing that with a free amine, we can get, or primary amine, we can get the azididine ring. And by employing this strategy, we're able to synthesize all of the piperazine isosteres in just 2 steps. And we can also extend this to other spirocycles containing other functionalities. And then we're not limited to cyclic ketones. We can start from acyclic substrates and access azididines containing all carbon quaternary centers. And just as a simple application, we aim to streamline the synthesis of this 2,6-diazospiro-3,3-heptane building block. This was previously reported by the Carrera lab and required 8 steps. And so if we start from azididinone, employ our dibromination, followed by cyclization, we can yield the differentially protected diazospirocycle. And then hydrogenolysis to remove the benzyl group completes our 3-step synthesis of this valuable building block on gram scale. And so overall, the bromination of Titanacyclobutanes has been shown to be a great way to rapidly access azididines. But I want to go back to this slide because we also realized that this iodine entry, where it was selected for the formation of the cyclopropane, was also interesting. And if we think about how you would transform a ketone into a cyclopropane, you would probably want to first do an olefination and then do a cyclopropanation. Here, we have an opportunity to do that in just one single step. And so I decided to develop that a little bit further with the help of a first year in our lab, Jacob Vins. And so we can start from a ketone, react with excess Tebbe's reagent, treat that with iodine, and yield the cyclopropane. This reaction is found to be very general. We can react with several different cyclic ketones to make spirocyclic cyclopropanes. And then when it comes to acyclic ketones and aldehydes, those also participate well to make the non-spirocyclic analogs. And then as this nice simple application, we aim to streamline the synthesis of this spirocyclic fragment used to prepare ladipasvir, which is a FDA-approved drug developed by Gilead Sciences used to treat hepatitis C. There's been several different syntheses reported. I've just showing 3 of the syntheses that are known. And you can see that given the simplicity of this fragment, these syntheses are relatively long and low yielding. And so we wanted to improve the routes to this fragment. And so when we employ our cyclopropanation, starting from as a commercially available ketone, we can access this chemotype in just a single step. And so now that we have a much better understanding of how to use titanium methylidene and Titanacyclobutanes, we wanted to really demonstrate the synthetic utility of this chemistry in a complex setting. And so to this end, we developed an enantioselective synthesis of fusicoccadiene. And so our lab has had a long-standing interest in natural products containing a 585 tricyclic scaffold, of which includes the ethiobolins and fusicosins. Both natural product families exhibit promising pharmacologies for anti-cancer treatment. And so I'll keep the focus of our strategy on the titanium-related transformations. And so what we envisioned in our synthesis of fusicoccadiene was a methylative ring opening of this dihydrofuran shown on the bottom right. And we envisioned accomplishing that via a Titanacyclobutane intermediate. And so, of course, this work couldn't have been done without the help of my coworkers, Vitaly and Jackie. And so I'm going to go through the entire synthesis, although we don't have enough time to dig into all the detail, but I encourage you each to read up on this paper if you would like some more details. And so the synthesis begins with an enantioselective aldol addition between furfural and acetone, and using Singh's catalyst, we're able to achieve 95% enantiomeric excess of this beta-hydroxy ketone. We then use that benzyl alcohol as a directing group for the diastereoselective 1,2 addition of ethynyl grignard. Next is a deoxygenation to remove the benzyl alcohol, and then we do a 1-pot hydroboration and Suzuki cross-coupling with this vinyl bromide to install the dienone. Next is a photocatalyzed cycloisomerization, and that enables the construction of the tricyclic core. And with that installed, it's just a matter of peripheral modifications to access our target. And we first start with a 1-pot alcohol acylation, followed by 1,4 addition to install the angular methyl group, which is isolated as the silyl-enol ether. That silyl-enol ether is then transformed into the enol triflate, and we use that enol triflate as a coupling handle in the palladium catalyzed Negishi cross-coupling to install this isopropyl group. And now we are ready for the methylative ring opening. And so I'll go in a little bit more detail a little bit later, but we're able to achieve this methylative ring opening by first treating with Tebbe's reagent, then isopropyl magnesium chloride on gram scale to yield this late-stage key intermediate in nearly 50% yield. And with completion of that, we have just 2 more steps to complete the synthesis. First is a dehydration followed by deprotection, then partial hydrogenation followed by another dehydration. And with that completes our 11-step synthesis of fusicoccadiene enabled by the methylative ring opening using this titanium methylidene chemistry. And overall, this completes each of the projects I was excited to share with you today. And I'd like to thank my group members for all their help throughout all these projects, as well as FSU facilities and NIH for the funding for each of these projects. And thank you all for listening.
So now, for our in-depth chemistry, Tyler's going to go over some of the mechanisms he developed in his synthesis.
First mechanism I'd like to go over is this photocatalyzed cycloisomerization. And so to do this reaction, we load a batch reactor with our polyene and iridium catalyst in toluene. We then irradiate that with light, which excites the dienone to the triplet state. This can then undergo an intramolecular stepwise cyclization to provide a cyclobutane. And once complete, we transfer that to another flask add some triethylamine. And and then we heat it to 110 degrees Celsius. This induces a cope rearrangement, and then because triethylamine is present, we can isomerize the double bond into conjugation to provide the enone. The other reaction I'd like to go over is the methylative ring opening. And so when we're thinking about how to do this methylative ring opening, we envisioned first forming this titanocyclobutane and then using that to induce a beta elimination. And so this type of chemistry is precedented, well precedented, as you can see in this example from Lawton's, in which they take an alkyl palladium species, which undergoes migratory insertion onto the alkene, leading to this intermediate, and then at refluxing temperatures, they're able to induce the beta elimination, similar to what we were trying to do. And so we thought maybe we could make this titanocyclobutane, raise the temperature to induce the beta elimination, and that could lead to the ring open product. However, we do not see any of this product form. And that is because, as I mentioned in the first couple of slides of this presentation, that the formation of this titanocyclobutane is in a degenerate metathesis equilibrium. Therefore, when heated, it actually just reverts back to starting material. And so we needed to figure out a way to get out of this degenerate metathesis equilibrium. So what we did to overcome this is using an exogenous nucleophile. And so after some optimization, we found that after forming the titanocyclobutane and treating it with isopropyl magnesium chloride, we can get the desired beta elimination. However, the mechanism doesn't simply stop here. What we found is an interesting radical cyclization occurs, which after recombination provides this cyclopropane intermediate. This can then undergo beta hydride elimination to provide a alkylidene cyclopropane, as well as a titanium hydride species. Then at elevated temperatures, this titanium hydride can decompose to form titanium-2. This can then undergo proximal insertion into the alkylidene cyclopropane to provide an alkylidene titanocyclobutane. And then this is then protonated during workup to provide the desired product. And if you would like to read a little bit more about each of these projects, this is the first paper I described, which was the halogenation of titanocyclobutanes to yield diisospirocycles and other azetidines. This is the paper for the direct ketone cyclopropanation using iodine as an electrophile. And then our more details about each of the steps that I briefly went over, as well as more understanding of each of these mechanisms, is described in our enantioselective total synthesis of fusicoccadiene published in JACS. Thank you all for listening.